20th International Physics Olympiad. Year 1989. IPHO. I offer private tutoring for preparation for physics Olympiads. I currently have openings. Write to me if you are interested. There is a discount for group lessons. My email is fred1996@hotmail.com. Problem 1. Boiling liquids. The solution to this problem can be found at the link in the description under this video. Consider two liquids A and B insoluble in each other. The pressures Pi, I equal A or B, of their saturated vapors obey, to a good approximation, the formula 1. Where P0 denotes the normal atmospheric pressure, T, the absolute temperature of the vapor, and alpha I and beta I equal A or B, certain constants depending on the liquid. The symbol ln denotes the natural logarithm, that is logarithm with base e equals 2.7182818. The values of the ratio Pi over P0 for the liquids A and B at the temperature 40 degrees Celsius and 90 degrees Celsius are given in Table 1.1. Question A. Determine the boiling temperatures of the liquids A and B under the pressure P0. Question B. The liquids A and B were poured into a vessel in which the layers shown in Figure 1.1 were formed. The surface of the liquid B has been covered with a thin layer of a non-volatile liquid C, which is insoluble in the liquids A and B and vice versa, thereby preventing any free evaporation from the upper surface of the liquid B. The ratio of molecular masses of the liquids A and B, in the gaseous phase, is gamma equal mu A over mu B equal 8. The masses of the liquids A and B were initially the same mass m, equal 100 gram. The heights of the layers of the liquids in the vessel and the densities of the liquids are small enough to make the assumption that the pressure in any point in the vessel is practically equal to the normal atmospheric pressure P0. The system of liquids in the vessel is slowly, but continuously, and uniformly, heated. It was established that the temperature T of the liquids changed with time tau as shown schematically in the figure 1.2. Determine the temperatures T1 and T2 corresponding to the horizontal parts of the diagram and the masses of the liquids A and B at the time tau 1. The temperatures should be rounded to the nearest degree in Celsius, and the masses of the liquids should be determined to 1/10 of gram. Remark: assume that the vapors of the liquids, to a good approximation. First, obey the Dalton law stating that the pressure of a mixture of gases is equal to the sum of the partial pressures of the gases forming the mixture and, second, can be treated as perfect gases up to the pressures corresponding to the saturated vapors. Solution to question A. A liquid boils when its saturated vapor pressure is equal to the external pressure. Thus, to find the boiling point of liquid I, where I is equal to A or B, we should determine the temperature Tbi at which Pi divided by beta I equals 1, then the logarithm of this expression is 0, and we get Tbi equals negative alpha I divided by beta I, expression 1. The coefficients alpha I and beta I are not explicitly indicated. However, they can be calculated using the formula given in the text of the problem. To do this, we should use the numerical data given in Table 1.1. For liquid A, we have expressions 2 and 3. After subtracting these equations, we obtain formula 4 for calculating alpha A. Thus, alpha A is calculated in expression 5. Now we can calculate the coefficient beta A using formulas 2 and 5, this will be the expression 6. So the boiling point of liquid A is equal to the expression 7, which is 349.95 Kelvin. In the Celsius scale, the boiling point of liquid A is equal to the formula 8, which is approximately 77 degrees Celsius. For liquid B, in the same way, we get the numbers 9, 10, 11. and the boiling point is 100 degrees Celsius. Formula 12. This was the solution to question A. Solution to the problem B. Since the liquids are in thermal contact with each other, their temperatures increase in the same way over time. At the beginning of heating, which corresponds to the left-hand slope of the diagram, no evaporation can occur. Free evaporation from the upper surface of liquid B is impossible. It is impossible due to the layer of non-volatile liquid C. Evaporation from within the system is considered below. Consider a bubble formed in liquid AA or in liquid B or on the surface separating these liquids. Such a bubble can form due to fluctuations or for many other reasons that will not be analyzed here. The bubble can leave the system only when the pressure inside it equals the external pressure P0, or when it is slightly greater than P0. Otherwise, the bubble collapses. The pressure inside a bubble formed in a volume of liquid AA or in a volume of liquid B is equal to the saturated vapor pressure of liquid AA or B, respectively. However, the pressure inside a bubble formed on the surface separating liquids AA and B is equal to the sum of the saturated vapor pressures of both of these liquids, since then the bubble is in contact with liquids AA and B simultaneously. In the case under consideration, the pressure inside the bubble is greater than the saturated vapor pressures of each of liquids AA and B, at the same temperature. Therefore, when the system is heated, the pressure P0 is achieved first of all in the bubbles formed on the surface separating the liquids. Thus, the temperature T1 corresponds to the general boiling of both liquids, occurring in the area of their direct contact. Temperature T1 is certainly lower than the boiling points of liquids AA and B, since then the saturated vapor pressures of liquids AA and B are less than P0, their sum is P0 and each of them is greater than 0. To determine the value of T0 with the required accuracy, you can calculate the values of the sum of the saturated vapors of liquids AA and B for several values of temperature T and C when you get the value P0. From the formula given in the text of the problem, we have ratios 1 and 2, respectively. PAA plus PB equals P0 when formula 3 is true, thus. We need to calculate the values of the following function. Expression 4, where T0 is equal to 273.15 degrees Celsius, and determine the temperature T1, at which y from T is equal to 1. When calculating the values of the function y from T, you can divide the intervals of temperatures T approximately by 2 and see if the results are greater or less than 1. We have table 1.2. Therefore, T1 is approximately equal to 67 degrees Celsius, with the required accuracy. Now we calculate the pressures of saturated vapors of liquids AA and B at temperature T1 is approximately equal to 67 degrees Celsius, that is, the pressures of saturated vapors of liquids AA and B in each bubble formed on the surface separating the liquids. From equations 1 and 2 we obtain the following approximate equalities. These pressures depend only on the temperature and, therefore, remain constant, as the bubbles move through liquid B. The volume of the bubbles during this movement also cannot change without violating the ratio PAA plus PB equal to P0. From the above remarks it follows that the mass ratio of saturated vapors of liquids AA and B in each bubble is the same. This conclusion remains valid as long as both liquids are in the system. After complete evaporation of one of the liquids, the temperature of the system will increase again, the second sloping part of the diagram. Then, however, the mass of the system remains constant, until the temperature reaches the value T2, at which the liquid, remaining in the vessel, begins to boil. Therefore, the temperature T2, the higher horizontal part of the diagram, corresponds to the boiling of the liquid remaining in the vessel. the ratio MAA to MB of the saturated vapors of liquids AA and B in each bubble leaving the system at temperature T1 is equal to the ratio of the densities of these vapors, ROAA to ROB. According to assumption 2, which states that the vapors can be considered as ideal gases. The latter ratio is equal to the ratio of the products of the saturated vapor pressures and the molecular masses. Expression 5. Thus the mass ratio is approximately 22.0. We see that liquid AA evaporates 22 times faster than liquid B. Evaporation of 100 grams of liquid AA at surface boiling at temperature T1 is associated with evaporation of 4.5 grams of liquid B. Thus, at time τ1, there are 95.5 grams of liquid B in the vessel, and no liquid AA. Temperature T2 is equal to the boiling point of liquid B, that is, 100 degrees Celsius. And temperature T1, as we found out, is approximately equal to 97 degrees Celsius. Remark: since the sum of the logarithms is not equal to the logarithm of the sum, the formula given in the text of the problem cannot be applied to a mixture of saturated vapors in bubbles formed at a surface separating liquids. However, the numerical data are chosen in such a way that even such an incorrect solution of the problem gives the correct value of the temperature T1, within the required accuracy. The purpose of this was to allow students to solve part B of the problem even if they incorrectly determined the temperature T1. This was the solution to question B. 20th International Physics Olympiad. Year 1989. IPHO. Problem 2. Rotating masses. 3 noncollinear points P1, P2, and P3, with known masses M1, M2, and M3, interact with one another through their mutual gravitational forces only. They are isolated in free space and do not interact with any other bodies. Let sigma denote the axis going through the center of mass of the 3 masses, and perpendicular to the triangle P1P to P3. What conditions should the angular velocities omega of the system, around the axis sigma, and the distances P1 P2 equals a 1 2, P to P3 equals a 2 3, P1 P3 equals a 1 3, fulfilled to allow the shape and size of the triangle P1P to P3 unchanged during the motion of the system? That is, under what conditions does the system rotate around the axis sigma as a rigid body? Solution to second problem. As the system is isolated, its total energy, that is the sum of the kinetic and potential energies, is conserved. The total potential energy of the points P1, P2, and P3 with the masses M1, M2 and M3 in the inertial system, that is when there are no inertial forces, is equal to the sum of the gravitational potential energies of all the pairs of points, P1, P2, P2, P3, and P1, P3. It depends only on the distances, a 1 2, a 2 3 and a 1 3, which are constant in time. Thus, the total potential energy of the system is constant. As a consequence, the kinetic energy of the system is constant too. The moment of inertia of the system with respect to the axis sigma depends only on the distances from the points P1, P2, and P3 to the axis sigma, which, for fixed, a 1 2, a 2 3 and a 1 3 do not depend on time. This means that the moment of inertia I is constant. Therefore, the angular velocity of the system omega must also be constant. Condition 1. This is the first condition we had to find. The other conditions will be determined by using 3 methods described below. However, prior to performing calculations, it is desirable to specify a convenient coordinate system in which the calculations are expected to be simple. Let the positions of the points P1, P2, and P3 with the masses m1, m2 and m3 be given by the vectors r1, r2, and r3. For simplicity we assume that the origin of the coordinate system is localized at the center of mass of the points P1, P2, and P3 with the masses m1, m2 and m3, and that all the vectors r1, r2, and r3 are in the same coordinate plane, that is in the plane x, y. Then the axis sigma is the axis z. In this coordinate system, according to the definition of the center of mass, we have equation 2. Now we will find the second condition by using several methods. First method. Consider the point P1 with the mass m1. The points P2 and P3 act on it with the forces in the expressions 3 and 4, where g denotes the gravitational constant. In the inertial frame the sum of these forces is the centripetal force F r1 equal negative m1 omega square r1, which causes the movement of the point P1 along a circle with the angular velocity omega. The moment of this force with respect to the axis sigma is equal to 0. Thus, we have expression 5. In the non-inertial frame, rotating around the axis sigma with the angular velocity omega, the sum of the forces, 3, 4, and the centrifugal force F prime r1 equal m1 omega square r1 should be equal to 0. Expression 6. The moment of this sum with respect to any axis equals to 0. The conditions, 5 and 6, are equivalent. They give the same vector equality. Expressions 7' and 7''. From the formula, 2, we get expression 8. Using this relation, we write the formula, 7, in the following form. That is, the vectors r1 and r3 are noncollinear. Therefore, the coefficients in the last formula must be equal to 0. The first equality leads to, and hence, A13 equal A12. Let they be equal to A. Then the second equality gives equation 9, where big M equal M1 plus M2 plus M3. Expression 10 denotes the total mass of the system. In the same way, for the points P2 and P3, one gets the relations A and B. Summarizing, the system can rotate as a rigid body if all the distances between the masses are equal. Expression 11. The angular velocity omega is constant and the relation, 9, holds. This was the solution to the problem in the first way. Second method. At the beginning we find the moment of inertia I of the system with respect to the axis sigma. Using the relation, 2, we can write expression 12. Of course, vector ri square equal r square for I equal 1, 2, 3. The quantities 2 rij for all rij can be determined from the following obvious relation 13. We get equation 14. With help of this relation, after simple transformations, we obtain expression 15. The moment of inertia I of the system with respect to the axis sigma, according to the definition of this quantity, is equal to 16. The last two formulae lead to the expression 17, where m, the total mass of the system, is defined by the formula, 10. In the non-inertial frame, rotating around the axis sigma with the angular velocity omega, the total potential energy V total is the sum of the gravitational potential energies 18 of all the masses and the potential energies 19 of the masses mi in the field of the centrifugal force. Expression 20. That is V total equal expression 21. A mechanical system is in equilibrium if its total potential energy has an extremum. In our case the total potential energy V total is a sum of 3 terms. Each of them is proportional to Fa equal 22. The extrema of this function can be found by taking its derivative with respect to a, and requiring this derivative to be 0. We get equation 23. It leads to 24. We see that all the terms in V total have extrema at the same values of a, ij equal a. In addition, the values of a and omega should obey the relation 24. It is easy to show that it is a minimum, because the second derivative is positive. Expression 25. Thus, the quantity V total has a minimum at a, ij equal a. This means that our three masses can remain in fixed distances only if these distances are equal to each other and relation between a and omega are in expressions 26. Where m the total mass of the system holds. We have obtained the conditions 9 and 11 again. That was solution by second way. Third method. Let us consider again the point P1 with the mass m1 and the forces F21 and F31 given by the formulae 3 and 4. It follows from the text of the problem that the total moment with respect to any fixed point or with respect to the mass center of the forces acting on the point P1 must be equal to 0. Thus, we have expression 27, where the symbol cross denotes the vector product. Therefore we have expression 28. But because cross product vector are 1 by itself equals 0, formula 29. From 28 we have 30. Using the formula 8, the last relation can be written as follows: next three equations. The vectors are 1 and are 3 are non-collinear, and different from 0. Therefore we have their cross product is not 0. It means a 1 2 equal a 1 3. And similarly a 1 2 equal a 2 3. And we have rederived the condition 11. Taking into account that all the distances a, ij have the same value a from the equation 7 concerning the point P1, using the relation 2, we obtain next three expressions. This is the condition 9. The same condition is got in result of similar calculations for the points P2 and P3. The method described here does not differ essentially from the first method. In fact, they are slight modifications of each other. However, it is interesting to notice how application of a proper mathematical language, that is the cross product, simplifies the calculations. That was solution by third way. 20th International Physics Olympiad. Year 1989. IPHO. Problem 3. Proton microscope. The problem concerns investigation of transforming the electron microscope with magnetic guiding of the electron beam, which is accelerated with the potential difference, U, equal 511 keV into a proton microscope, in which the proton beam is accelerated with the potential difference, U. For this purpose, solve the following two questions. Question A. An electron, after leaving a device, which accelerated it with the potential difference, U, falls into a region with an inhomogeneous field, B, generated with a system of stationary coils L1, L2, etc. till Ln. The known currents in the coils are I1, I2, etc. till In, respectively. What should the currents I1 prime, 2 prime, etc. till In prime in the coils L1, L2, etc. till Ln be, in order to guide the proton, initially accelerated with the potential difference, U, along the same trajectory and in the same direction as that of the electron? Hint: the problem can be solved by finding a condition under which the equation describing the trajectory is the same in both cases. It may be helpful to use the relation 1. Question B. How many times would the resolving power of the above microscope increase or decrease if the electron beam were replaced with the proton beam? Assume that the resolving power of the microscope, that is the smallest distance between two-point objects whose circular images can be just separated, depends only on the wave properties of the particles. Assume that the velocities of the electrons and protons before their acceleration are zero, and that there is no interaction between own magnetic moment of either electrons or protons and the magnetic field. Assume also that the electromagnetic radiation emitted by the moving particles can be neglected. Note, very often physicists use 1 electron volt, and its derivatives such as 1 kilo electron volt or 1 mega electron volt, as a unit of energy. 1 electron volt is the energy gained by the electron that passed the potential difference equal to 1 volt. Perform the calculations assuming the following data. Rest energy of electron is 511 kilo electron volt. Rest energy of proton is 938 mega electron volt. Solution to problem 3, solution to part A. At the beginning one should notice that the kinetic energy of the electron accelerated, with the potential difference U equals 511 kV equals to its rest energy E0. Therefore, at least in the case of the electron, the laws of the classical physics cannot be applied. It is necessary to use relativistic laws. The relativistic equation of motion of a particle with the charge E in the magnetic field B has the following form. Expression 2, where P equals m0 gamma v denotes the momentum of the particle as a vector and FL equals Ross product EV by B. Expression 3 is the Lorentz force. Its value is EVB and its direction is determined with the right-hand rule. m0 denotes the rest mass of the particle and v denotes the velocity of the particle. The quantity gamma is given by the formula for, the Lorentz force FL is perpendicular to the velocity v of the particle and to its momentum P equals m0 gamma v. Hence, dot product FL by equals dot product FL by P equals 0. Expression 5. Multiplying the equation of motion by P and making use of the hint given in the text of the problem, we get, expression 6, it means that the value of the particle momentum, and the value of the velocity, is constant, during the motion. P equals m0 v gamma is constant and v equals constant. The same result can be obtained without any formulae in the following way. The Lorentz force FL is perpendicular to the velocity v and to the momentum P as P equals m0 gamma v and, as a consequence, to the trajectory of the particle. Therefore, there is no force that could change the component of the momentum tangent to the trajectory. Thus, this component, whose value is equal to the length of P, should be constant. The same refers to the component of the velocity tangent to the trajectory as P equals m0 gamma v. Let S denotes the path passed by the particle along the trajectory. From the definition of the velocity, we have delta S over delta T equals v, equation 7. Using this formula, we can rewrite the equation of motion as 8 and 9. Dividing this equation by P and making use of the fact that P is constant, we obtain 10 and hence 11. Where T is the versor, unit vector tangent to the trajectory. The above equation is exactly the same for both electrons and protons if and only if the vector quantity 12 is the same in both cases. Denoting corresponding quantities for protons with the same symbols as for the electrons. But with primes, one gets that the condition, under which both electrons and protons can move along the same trajectory, is equivalent to the equality 13. However, the Lorentz force is proportional to the value of the velocity of the particle, and the directions of any two vectors of the following three, t or v, fl, b, determine the direction of the third of them, right-hand rule. Therefore, the above condition can be written in the form of 14. Hence we have 15. This means that at any point the direction of the field, B, should be conserved, its orientation should be changed into the opposite one, and the value of the field should be multiplied by the same factor p prime over p. The magnetic field, B, is a vector sum of the magnetic fields of the coils that are arbitrarily distributed in the space. Therefore, each of this field should be scaled with the same factor negative p prime over p. However, the magnetic field of any coil is proportional to the current flowing in it. This means that the required scaling of the fields can only be achieved by the scaling of all the currents with the same factor negative p prime over p, equation 16. Now we shall determine the ratio p prime over p. The kinetic energies of the particles in both cases are the same, they are equal to expression 17, which is 511 keV. The general relativistic relation between the total energy E of the particle with the rest energy E0 and its momentum p has the form 18, where c denotes the velocity of light. The total energy of considered particles is equal to the sum of their rest and kinetic energies. Expression 19. Using these formulae and knowing that in our case Ek equals Eu equals Ee, we determine the momenta of the electrons, p, and the protons, p prime. We get for electrons 20 and 21. And for protons 22 and 23. Hence p prime over p equals about 35. 0, expression 24. And In prime equals negative 35.0 In, expression 25. It is worthwhile to notice that our protons are almost classical, because their kinetic energy Ek equals Ee is small compared to the proton rest energy Ep. Thus, one can expect that the momentum of the proton can be determined, with a good accuracy, from the classical considerations. We have formulae 26 and 27. On the other hand, the momentum of the proton determined from the relativistic formulae can be written in a simpler form since Ep over Ee much greater than 1. We get p prime approximately equals expression 28. In accordance with our expectations, we have obtained the same result as above, that was solution to part A. Solution to part B. The resolving power of the microscope, in the meaning mentioned in the text of the problem, is proportional to the wavelength, in our case to the length of the de Broglie wave. Lambda equals h over p, expression 29. Where h denotes the Planck constant and p is the momentum of the particle. We see that lambda is inversely proportional to the momentum of the particle. Therefore, after replacing the electron beam with the proton beam, the resolving power will be changed by the factor p over p prime, which is approximately 1 over 35. It means that our proton microscope would allow observation of the objects about 35 times smaller than the electron microscope. Remarks and typical mistakes in the pupil's solutions. Some of the participants tried to solve the problem by using laws of classical mechanics only. Of course, this approach was entirely wrong. Some students tried to find the required condition by equating accelerations of particles in both cases. They understood the acceleration of the particle as a ratio of the force acting on the particle to the relativistic mass of the particle. This approach is incorrect. First, in relativistic physics the relationship between force and acceleration is more complicated. It deals with not one relativistic mass, but with two relativistic masses, transverse and longitudinal. Secondly, identity of trajectories need not require equality of accelerations. The actual condition, that is the identity of E, B, over P in both cases, can be obtained from the following two requirements. First, in any given point of the trajectory the curvature should be the same in both cases. Second, in the vicinity of any given point the plane containing a small arc of the trajectory should be oriented in space in both cases in the same way. Most of the students followed the approach described just above. Unfortunately, many forgot about the second requirement. They neglected the vector character of the quantity EB over P. That was solution to part B. And we finished discussion to problem 3.